Okay, so for task number 1, we are going to draw a chiral compound, and we're going to draw its enantiomer. So for a chiral compound, we have to have a carbon at the center, and we can have a tetrahedral at the carbon, and we're going to draw 4 different substituents coming out of it. Okay, so we have a fluorine, we have a chlorine, bromine, we have a hydrogen. Chlorine is wedged, it's coming out of the page, and the bromine is dashed, it's behind the page, right? So for us to find its enantiomer, we have to first find its mirror image, and then we have to make sure that it's non-superimposable upon the original compound. So we can first find the mirror image. That's a bad drawing. This would be a longer line right here, so the carbon in the middle. But this is the mirror image of this compound. So now we can already kind of see that it's going to be non-superimposable upon, but we can even rotate it 180 degrees and we can check. So when we do that, right, so this is non-superimposable upon the original one. You know, the bromine switches from being behind the page to out of the page. Same with the chlorine, it switches. So we know it's going to be non-superimposable, and this is also a mirror image of it. So this is going to be an enantiomer. We also notice that all the chirality centers switched, right? So we already know that all the configurations of the chirality centers have switched. So it's going to be an enantiomer. Okay, so a diastereomer. It is a type of stereoisomer that are not mirror images of each other. So they have the same molecular formula and the connectivity of atoms, but they differ in the spatial arrangement of those atoms. And then, so unlike enantiomers that are mirror images of each other and they have the opposite configurations, right? So diastereomers are going to be not mirror images of each other, and they have at least one chiral center that is different while the others will stay the same, right? The configurations, the chirality center, one is going to be different. So we can draw one first. Draw this. So we have 2 chlorines wedged coming out of the page, or towards us. So to draw a diastereomer, we just have to draw one. We have to switch the configuration on one atom, making them not mirror images of each other. So it differs in spatial arrangement. One of the configurations on one of the chirality centers has switched. So now we know that this is a diastereomer. These are both diastereomers of each other. So, yeah. So let me get up the next question. What? Okay, sorry. Got to pull up the instructions. Draw example of a meso compound. Okay, so first task is to draw a meso compound. So to do that, well, a meso compound, what it is basically is a compound that all the chirality centers have changed, like an enantiomer, right? But the compound is symmetric, so it's achiral. So due to the symmetry, and it being a chiral, it's now going to be a meso compound and not an enantiomer. So what we can do is similar to the ones we just drew. So, like an enantiomer, right? All the configurations at each chirality center are going to switch. But what we notice is we can split this right in half, right? There's symmetry. So, when there's symmetry, it can't be chiral. So this is going to be achiral, and these are going to be they're going to be meso compounds, right? Because of their symmetry, right? So all meso compounds are chiral, right? Because their internal symmetry allows them to be superimposed on the mirror images, but this inherent symmetry prevents them from being distinct and enantiomers, right? But not all achiral compounds are meso. So like we can consider like butane. Right? So if we were going to call it, we can call it any of these like a chiral center for now. But I mean, it's achiral, right? But at the same time, we notice that this carbon right here, it's attached to two hydrogens, right? So off the bat, we already know, not a chirality center, right? Because we have to have 4 different constituents. And then we have 2 CH3, so I mean, even worse. But like, so it's achiral, but it doesn't have any chiral centers at all. So an achiral compound can exist. An achiral compound can exist, right? Because it has symmetry, but it can exist without chiral centers. So then it doesn't even require symmetry. So not all achiral compounds are meso, right? Okay, let me get the original. Okay, so determine. All right, so for the last task, we will determine the RS configuration of the following compound. So to do that, we can first find the chiral center. So a chiral center is a carbon, it's a tetrahedral, it has 4 different constituents. So we have one right here. I mean, the other ones, we have, there would be no other possible ways for a chirality center over here besides this one. So we're gonna look right here. Right, so the carbon is attached to an oxygen, which is then attached to a carbon, and then over here we got this connect to this, and then this connect to a carbon, and we have this connect to a carbon as well. We have 4 different constituents here, right? Because this is going to be double bonded to an oxygen. We have an oxygen here. We have a hydrogen here. We have this, which is attached, which is then double bonded to an oxygen. And we have this, which is then attached to a methyl group, right? So we have different ones. And now our first step would be to find the priority of each group, right? So the highest on the table is going to be the highest priority. So we already know oxygen is going to be number 1. Hydrogen is going to be number 4. And then we have 2, 3, and equal these carbons. And we can break the tie. So this carbon right here, we have 1 carbon that's attached. So the C is attached to this C, which is attached to, C, 3 H's, right? It's attached to 3 H's. And this other one is going to be attached to a C. It's going to be double bonded to an oxygen. So we can compare these groups, right? So this carbon double bonded to an oxygen and it's attached to a carbon. This one's attached to a carbon and which is attached to 3 hydrogens. So we know this one's going to be higher priority, right? Because it's attached to an oxygen which is higher than all the hydrogens. So the tie number 2 would equal the C that's double bonded to O, and then fall in line would be the other carbon. Okay, so now we want to find if it goes counterclockwise or clockwise, right? So the first thing we can do is we can order the substituents on here. We have 1, we have 4, 2, 3. So the problem here is that this oxygen right here is behind the page, and we want the ones of highest priority to be in the front. So we can then rotate this and we can make it so the oxygen is now coming out of the page. So do that. I'm just going to erase this. Okay, so first, so we can switch this right here. Right, so we're gonna start by that. We're gonna rotate it 180 degrees, and then we're gonna go from there. So this is going to be attached to the carbon, which is then going to be right, and sorry, did that wrong. Okay, so we're here, right? And then we're going to go down the hydrogen, right? And then, so this was dashed, and now this is going to become wedged. Sorry. Right, so the oxygen has become wedged, and then we're going to have this coming up. So this is going to be behind the page, and you know, best case scenario, we'd be able to make the hydrogen be behind because it's the lowest priority, right? So we got 4, 1, 2, 2, 3. So now we have the one of highest priority in the front, right? So now we can start at 1 and we can go in the order ignoring number 4. And we went counterclockwise. So this is going to be S configuration. I hope you enjoyed.